Okay, so we're going to finish up the fundamental theorem of calculus. The author has it backwards. I don't see how you can do this without doing the first part that we did yesterday. And yesterday, and we should go back and review that for a second, what was yesterday's fundamental theorem of calculus? Well, first we had Riemann, and actually we did this yesterday and we did it Friday. And he said, if I have the limit as n goes to infinity, and I want to find the area under the curve, then I'm going to add up all these really tiny rectangles. Add them all up, and it's going to be an infinite number of rectangles, and it's f of x by delta x. And you should see a base and a height in that formula where delta x is the base and f of x is the height. So he said, I don't want to write that. I'm writing with my left hand. I don't want to write it either. So he made up a symbol that means add up all the areas of all the rectangles. That's what that does. F of x dx. And then Newton and Leibniz, and Newton might have been the first one, I'm not really sure, discovered a relationship between the area under the curve and an antiderivative. And so we found out that if I take this area under the curve and I find the antiderivative of my function, we'll call it capital F of x, and evaluate it at the endpoints, I'll actually get the area under the curve. So why it would be an antiderivative is beyond me. And why just the endpoints? Why does that give you the area? It's another good question. And that's the fundamental theorem of calculus part 1. This is what the author says it's part 2, but I don't really care. Just remember it's FTC. And you're going to use it on the exam. I guarantee both this and the next part that we're going to do. Okay, so that's all you do, is you find the antiderivative of little f of x and evaluate that antiderivative at the endpoints. Okay, so that's old. We should know that. I don't know if we do, but we should. So let's practice a little bit with antiderivatives, because this is as hard as the quiz. And let's find the antiderivative of this. Notice what we're going to do. We are going to find the derivative of the antiderivative. And you should be thinking, what should happen? What do you think happens? What if I take the derivative of an antiderivative? What did you say? You get what you started with. Pretty much that's it. Let's actually see if that's true. So I'm going to take the derivative with respect to x. It's a little complicated when you have chain rule here, but we'll get there. And then find the antiderivative of t cubed. And that's what you have to know for tomorrow. What's the antiderivative of that? T to the 4th over 4. And then the antiderivative of 2t squared is 2 t to the what? 3rd over 3, right? Plus 4t. If you do the homework out of this section, you should be just fine on the section 5.4. This is where we said 5.3. Even the examples we did in 5.3 should be fine. And then you're going to do what? We're going to evaluate this at 1 and x. So we'll go ahead and evaluate it. We still have a derivative to take, just not yet. So it's b dx. And it's going to be, I'm going to put x in there, so it's x to the 4th over 4 plus 2x cubed over 3 plus 4x. That's the first part. And then it's going to be minus, and I'm going to use parentheses because I want to get it right. And it's 1/4 plus 2/3. Actually, I don't care if I get it right. You'll see why in a second. Plus 4. And what happens when I take the derivative of this number here at the end? Because remember, now I anti-differentiated, now I'm going to take the derivative again. What happens to the derivative of that thing? It's 0, so I really don't care if I did do it right, actually. And now if we find the derivative of this, and notice what happens, the derivative of x to the 4th over 4 is just x cubed, right? Plus, and what happens to the 3's here when I take the derivative of 2x cubed over 3? The 3's cancel out. I'm left with 2x squared plus 4. interesting. It's the same function, but not at t, but at what? X. So I substitute X for t. And you might be thinking, well, why would I ever take the derivative of an antiderivative? What's the point of that? Because a lot of times you're never given the function. You're given information about the function. And if I wanted to show that I had a max or a min, or at least a critical point, and I define my function to be the area under curve, then the derivative would be what I'd have to do, the derivative of the antiderivative. But we'll see that on Thursday. Okay, now let's do problem 2. It's the same as problem 1. See if I can do that. There it is. Let's see if I can clone that. But we're not going to evaluate it. That was the wrong thing. There. We're not going to evaluate it at X. Where are we going to evaluate it at? Obviously, we can't go with it. Can I do that? I can't. I'm going to evaluate it. I don't want to go the wrong thing. There. Not at X, but where? At X cubed plus 1. So when I put it in, I'm just going to come down here where I have some space. Then I have the derivative with respect to X. Hopefully it's enough space. And I'm going to put this in for t. Not X now, it's X cubed plus 1. So it's X cubed plus 1 to the 4th over 4 plus 2 X cubed plus 1 cubed over 3, and I'm going to be lazy, plus 4 times X cubed plus 1 all of that, and then it's minus this constant again. Can I just call it a constant? Because what's going to happen when I take the derivative of it? It's 0. Okay, take the derivative. Well, I'm going to get the same thing I did before, kind of. The 4's are going to go. I'll be left with X cubed plus 1 to the what power? I'm going to do the power rule here with the outside function. So it'll be the 3rd, and then what do I have to do? I have to multiply it by the derivative of the inside. Chain rule. So the derivative of the inside is what? 3x squared. That's why we want to do this, so you can see what happens. What happens to the 3's when I take the derivative here? They cancel, so I'm left with plus 2 x cubed plus 1 times, and then the chain rule, times the derivative of the inside function, which is 3x squared, plus, and then I'm going to take the derivative of this, which is 4, times the derivative of the inside function, which is 3x squared. Now, if you notice, everything in green is exactly like what we have over here. But in place of x, you're going to have x cubed plus 1, and then you have to multiply it by the derivative of that upper limit. Yeah. Oh, it should be squared. Yeah, I did that twice today. I just get messed up. Well, that's all there is. What does a derivative do to an antiderivative? It just undoes it. Get back to your original function. However, when this upper limit is a variable, then if you were to actually integrate this, you're going to have this composite function, and you have to take it times the derivative of whatever you put in there. That's the problem. So shall we try some problems here that you cannot integrate? You don't have the tools to do number 3, and I'm not sure number 4 is even possible. So if you do the assignment by integrating and differentiating, it's going to take you a long time to get done. So let's not. So what's the answer to this one? You're going to take x and put it right in there for t. because the derivative will undo that integral. It gets rid of it. So what's the answer here? Not e to the t, but e to the x cosine of x. Is there any work to show? No. So if you show work, then that's because you're doing it wrong. How about this one? It's going to be 1 over, and it's the square root of t squared plus t. And what am I going to put in there for t? Not an x this time, but what? X cubed. And do not simplify, because if you do and you do it wrong, you're in trouble. Like, the only reason why we'd have to do that would be for multiple choice. That is not x to the 5th, it's x to the 6th. Oh, what did I forget to do? Remember, if you did integrate this, you would have some function with an x cubed in it. You have to do the chain rule when you differentiate. So it's times what? The derivative of the upper limit, which is 3x squared. Because if you were to integrate this, you would have some function of x cubed. So when I take the derivative of my antiderivative, evaluated at x cubed, then that would be f prime of x cubed times what? The derivative of the inside function, which is 3x squared. If I were to do it. Which is the reason why I took the time and did this problem. But when you anti-differentiated it, you had this x cubed plus 1. So when you take the derivative back again, you still have to do the derivative of the inside function. So let's try another one. Oh, I did that already. That one. It's the same one we just did, but you probably won't see it. All you do is you take x cubed plus 1 and substitute it right in there for that t and that t. And so I'm going to get x cubed plus 1 cubed, right? Plus 2 x cubed plus 1. I'm not going to forget my squared. Plus 4. So all I do is substitute this into this function, and then I have to multiply it by the derivative of the upper limit, which is 3x squared. That's all there is. So we'll do some more problems. So summarize it and then write it out in words, and then we'll do a couple more problems, and then you have work time. So it shouldn't be too bad. I'll get back to your homework as well. Okay, so what's the derivative of the antiderivative? And notice it starts at a constant. It doesn't matter what the constant is. So this theorem only works if you start at a constant. So if it's backwards, you're going to have to do some fixing. What's the derivative of the antiderivative then? This is just what? F of x, that's it. So nice. What's this one? I want the, and this is the same thing, sorry. This is going to be f of what? G of x times g prime of x. Oops. That's all it is. So in words, use my right hand. The derivative of an antiderivative oops. So the derivative of an antiderivative is the function, can I just do that? Evaluated at the upper limit We'll hit on this again tomorrow. And then, so I'm going to take this, I'm going to put g of x into my function there, so I'm going to evaluate f of x there, or f of t actually, and then I'm going to multiply some of these times the derivative of the upper limit. That's all it does. Derivative undoes an antiderivative. The only thing that's confusing is that chain rule. And then you have to have it in the right form. So what's the answer to number 5? This is how you're going to do your homework. 6 is trickier, but 5 isn't so bad. What's the answer to that? It's the sine of what? Cosine. That's it. That's all you have to do. Well, times the derivative of the upper limit, which is negative sine of x. So it's easy. It's really easy. Okay. So this one has a problem. 6 has a problem because it's not starting at a constant. So what I can do, kind of cheat a little bit, I can break that using the additive property of integrals. I can break that into 2 integrals. So I'm going to take the derivative, and we're going to go from sine of x to some constant. It doesn't really matter what your constant is, so I'll call it 0. It makes no difference. Of u squared du plus, and then it's the derivative with respect to x of the integral from 0 to cosine. And it's u squared du. Well, the problem with the first integral, it's in the wrong order. Remember, it has to go from the constant first. The fundamental theorem of calculus is f of b minus f of a. So that's subtraction, so that's not commutative. So it does make a difference that that's in the wrong order, but what can I do as properties of integrals? I can do something, can't I? Yeah, make it negative. And so it will be negative and integrate from 0 to sine of x of u squared du. If you can go faster than me, that's great. Plus, and we could go ahead and do this one. What's this going to be? You're just going to substitute cosine of x in for u, so it's going to be cosine of x what? Squared times the derivative of the cosine function, which is negative sine. And now we just have to do the first one, and that's a negative, and I'm going to substitute sine in there, so it's going to be sine of x squared times, and then I have to do the derivative of the upper limit, which is cosine of x. And then still plus this other side. And cheat. There. That's it. It's really not that bad. It's one of our favorite theorems. Mrs. Herford loves this one. But I guarantee it's going to be on the free response on the test, in the exam. You will see a practice one on Thursday. And actually 57 through 60 are like the problems on the test. So all that's left is just to quickly review properties, and I'm not going to actually go through them. These are the properties we already did. And this in particular is the mean value theorem. So 3 is the mean value theorem. Here we talk about if you switch from A to B to A, put a negative sign there. Number 5, the area under a curve at one point is 0. And this is a Riemann sum. It's the definition of a definite integral. And then on the next page, which you still have, that's the fundamental theorem of calculus. And then for other properties of integrals, you can pull the k right through the integral sign. You can distribute the integral over a sum or a difference. Just can't distribute over multiplication. And this is the additive property of functions. It's geometry. And that's all I have to say. I need to do any problems with you, or just give you work time? Okay, so please use